All right, everyone, let's get started. So we were talking about optimization, and we studied the gradient, studied linear approximations, and now we're in a position to use some of those things productively to come up with an algorithm that can be used to find the parameters that minimize the cost. And the simplest form of this algorithm is just called gradient descent. And this is sort of the workhorse idea behind just about all the machine learning optimization algorithms. And it can be described very simply by this idea. You choose an initial parameter vector, call it W0, and then you iteratively take steps where what you do is you take that parameter vector, you subtract the gradient times a small number alpha k. That moves you downhill, and then you evaluate the gradient at the new point. You move downhill again, evaluate the gradient at the new point, move downhill. And if you keep doing this, then asymptotically you will reach the minimum, or at least the closest minimum to where you started if there's multiple minima. So that's the idea. We call this alpha k the step size or the learning rate. We did a little analysis of gradient descent where we convinced ourselves that if you look at the cost after the update, that's the cost before the update, and then we have a term here which decreases the cost, which is good because we want the cost to go down. This is guaranteed to be negative. But then we have this part here which increases the cost because this is positive. So that's bad. And so in order for this to be lower than this, we need to make sure that overall this is negative, or from another perspective that this term overwhelms this term here. And essentially that means that alpha k must overwhelm c times alpha k squared. And for that to happen, so yeah, basically this order of alpha k squared means there's some unknown constant c, so that when alpha k is close enough to 0, this whole thing is less than or equal to c times alpha k squared. So basically if we choose alpha k less than 1 over c, then that means that this term will be smaller than this term, meaning that this negative thing will overwhelm the positive thing, meaning that this cost after our update will be smaller than the cost before the update, and that's exactly what we want. Okay, so that's sort of convincing ourselves that gradient descent works, but also that we need the step size to be sufficiently small. And if the step size is not sufficiently small, essentially what can happen is we can take a step in the gradient direction, but maybe we take a step all the way over here, and now we see that the cost is actually greater than the cost where we started. So as long as we take small steps that don't overshoot, we can eventually get to the minimum. All right, any questions on these ideas? Okay, everybody go with these? All right. We talked a little bit about local versus global minima, in the sense that functions in some cases can have multiple minima, and if you start gradient descent in this region here, what would happen is it would converge down to this local minimum if you use this small step size. But maybe what you want to happen is you want it to converge to this global minimum. So one way to avoid that is if you are using a convex function, then this won't happen because any local minimum is a global minimum. I think we'll be able to talk about convexity later today at the end of the lecture, so we'll get back to that. And the nice thing is that many of the cost functions that we've been working with, like this cross entropy loss here, this one is convex, so we don't have to worry about the presence of bad local minima and so on. So we were working on gradient of cross entropy loss. This is something we know we can ask sklearn to solve this problem for us, but we'd like to understand how we solve this ourselves, because that's useful and that will help us understand things we're going to do in the next few units. So our objective is to find the parameters w that minimize this loss. We'll call it J of W. And this is a little bit complicated because, number one, there's nonlinearities here, and number two, we have many parameters, and those many parameters all get kind of mixed together into this loss. So we said a nice way to break this apart into two simpler problems is to first to think about this as one stage of the function taking you from W to J. And in this first stage, you do this for all the i's, and you get that the scores equal A times W. So what's nice about this is a linear transformation. As we know, linear transformations are simpler than nonlinear ones. So this is a convenient thing. And then once you have the z's, then this part, even though it's nonlinear, it's separable in that this is a sum of terms that each depend only on a single one of your zi's. They don't mix all the zi's together. They operate independently on the different zi's. So that's convenient. Linear transformation followed by separable function. And this is actually a pretty common thing that happens in machine learning. So it's a structure that we would like to learn how to work with. And essentially, so we're going to think of our J of omega as this two-stage. First, we go from J of W. First, we go from W to Z, then from Z to F, or in this case, F is J. The reason why I'm using F is because we're saying if J is defined on the W's, F is defined on the Z's, so it's just sort of a notational thing. I wouldn't want to write J of Z. That I think could be a little confusing because J here is defined as a function of W. Okay, so actually there is, along those lines, this really should say dj here. J is our function of W. So we can write dj, which is obviously the thing we need in order to run gradient descent. We need to be able to compute these gradients. So we can compute them using this multivariable chain rule, which is super important. And we'll be using it a lot going forward. So it basically says, I think I had a visualization. Let me go to my previous visualization of this. Yeah, had a visualization here that showed that if you have different parameters W and different intermediate variables Z, and they all affect some final scalar output, when you want to know the gradient of this with respect to this, you have to think of all the ways that information can flow. And essentially, you have to sum over these products of gradients. That's essentially what this is doing here. It's looking at all the different ways the information can flow from W to J. Okay, so coming back here, this is how we're going to compute our gradients. And so we have to just look at these two terms here. Both of them are pretty straightforward. Based on this definition of F here, we can get dF dZi. We solved for this last time. It wasn't too difficult. And then based on this here, when we look at the ith element of Z and the jth element of W, we get the dZi dWj. It's just Aij, the ith row and jth column of A. So these are the two building blocks that we need to put together here. And here we wrote a little function to do this in Python. And to prepare for the details of that function, what we did is we wrote F in a slightly different way that allowed us to use this quantity several places. This is a quantity that also shows up in the gradient, so we can compute that once and then use it for several things. And then this is the multivariate chain rule from the previous page where we already solved for those expressions. Here we're plugging in one of them. Here we're plugging in the other one from the previous page. And then we're just essentially rewriting this as a matrix vector multiply A transpose times the gradient of F. That's a vector. And basically that's what we see here. A transpose dot df dz. That's doing this multiply. Okay, so that's where we were last time. And yeah, one other thing too is when we write these functions like this that compute the gradient for gradient descent, we typically split them into a forward pass and a backwards pass, at least conceptually. In the forward pass, what you do is you compute all these intermediate variables. So you're given the w's, you first compute the z's, then you compute the cost, which you evaluate using f on the z's. Once that's all done, now you can compute the gradients. That's what you do in the backwards pass. And here, we're just using that multivariate chain rule, and this is essentially what we need to do in the backward pass. So this function computes both the cost and the gradient. And that's important because when we run gradient descent, we want to see how the cost is decreasing to make sure we've run it for enough iterations or to see whether it's working well or not. So it's important to have both. And also, computing both of them together is often very convenient because they tend to rely on a lot of the same quantities. So computationally, it's very convenient. If you're going to do one, you may as well do the other. Okay, so I think that's where we were. Any questions on anything so far? Okay, so now just a couple little programming things. So the function that we got on the previous page was basically this, and you can see it takes in three things. It takes in the current parameter vector w, at which you're going to evaluate the cost and the gradient, but it also takes in the training quantities x and y, and clearly the cost and the gradient will depend on those. But when we actually program gradient descent, we might think of this x and y as being sort of not really that interesting for us. We just want, for gradient descent, we just want a function of w. And so this is really just a coding thing. And there's basically two ways to go about this. One really simple, straightforward way is to create what's called a lambda function. And if you're familiar with anonymous functions in MATLAB, they're the ones that look like this. It's exactly the same idea, but in Python it's called a lambda function. So essentially it goes like this. You start with the function here that has all three parameters, and then you just say, let's make a new function out of this that depends only on w. And so what that means is the values of the training x and y are going to be hard-coded into this function jeval. So when you call that function is simply a function of the parameters w, and it's hard-coded for the values of x and y that you assigned when you made this function. Does that make sense? So it's really not much that we're doing. We're just rewriting this so that it doesn't explicitly depend on those two last outputs, because that's going to be a little bit more convenient for our coding. It helps to decouple the optimization part from the training data part. Okay. Is everybody good with that? All right. So there's another way to do this, and it's a little bit more sophisticated, and it's the way that things tend to be implemented more commonly, which is to make a Python class. And so here's this class we're making. I think you guys all have taken object-oriented programming, so you're probably familiar with these notions, and we've been working with them throughout the course with many of the sklearn functions, or objects maybe. But a class is basically, it's this object that has within it several functions, but it can also have data stored within it. And in Python, this is always going to have what we can call an initializer or a constructor. This is a little function that is called when you instantiate the class. So we're going to make this class called logistic function. When we instantiate it, we're going to give it our data, training data x and y. And it's going to return this object log fun. That object will have the data stored inside, right? Because it's going to be stored. The reason we're giving this data to it is so it can store it. But it's also going to have functions. So for example, it's going to have our jeval, which is the function like this, but without the x and the y's. So if you want to evaluate the cost and the gradient of this log fun at a particular point, you do log fun dot, and then it goes through and it finds among its lists of functions, it finds this jeval function here. Okay. And you can add additional functions if you want. You can add as many as you want, and then you'll have many other dot things. And you probably recognize this. We see this all the time with NumPy, with sklearn. There's this object, and there's dot this, dot that, all these different functions. So they're created in this way. So let's take a look at what happens in this constructor. So the constructor, again, it's the thing that's run when you instantiate the class. So in the constructor, you're giving it the x and y training typically, and what it's doing here is it's basically storing that as a parameter of this class. Self.x is assigned to x. So now that it's self.x, that thing is stored inside this object. Same thing with y, self.y equals y. Now this, we're going to find the number of samples in our training data set, x.shape0. We could store this as self.n, but we're not going to. We don't really need to. So we're just going to think of n as a temporary variable. But what we're going to do with it is we're going to make a ones vector that has n elements in it, stack that next to our x vector. So here's our ones vector, stack that next to our x matrix, and we're going to call this A. But we are going to store A as self.A. Okay, so now the internal variables will be x, y, and a. And when we run this jeval function, you can see jeval inherits all the self stuff. So jeval will know whatever is in that self structure. So for example, the first step in jeval is to compute the score vector z with this matrix multiply a.w. But here, it's using self.a. That's the variable that it knows about, the variable we created here. Other than that, these commands are exactly the same ones that we saw over here. So it's just doing the same thing. It's evaluating the cost and gradient. Okay, so these are two ways to do it. This is the more official way, much more flexible. But this is a very quick way if you don't want to go through with building a whole object. All right, any questions on, yes?
If we're saving A, why do we need to save X?
It's a good point. I guess we don't, at least for the purposes of this, we don't really need to save X and Y. I can't remember if we do. Sorry?
Y is used, like in J.
Oh yes, Y is used, but it looks like X is not used, right?
Yeah, because it's in A.
Right. So perhaps we didn't actually need to store this. Could have gotten away without it. As far as I know, we're probably not going to build anything else, any other functions that use X. So yeah, good point. Okay. All right. Any other questions so far? All right. So now here's a thing I highly recommend. Anytime you program a function like this one, where maybe you had to derive some gradient expression, and then you had to program the gradient expression. It's easy to make mistakes. We all make mistakes, right? The key point is that we can detect when we made a mistake so that we can correct for it. Because if you don't know whether you made a mistake, that's the worst case, right? You don't even know whether you're correct or not. So there is a nice way, whenever you make a piece of code that computes the gradient, the cost and gradient, there's a nice way to make sure that at least the cost and gradient are consistent. And what you do is you choose two random points, we'll call them W1 and W0, that are close together. And then you exploit this Taylor series approximation. This is just the linear approximation we derived earlier, right? This should hold for any W1 that's close to W0. It should hold pretty closely. So if this holds, then what that means is I can move this to the other side, and we get this expression. So what we've done here is we've taken a random initial point. So this is just finding how many features we have D, making a W vector of dimension D plus 1. Notice we're using rand n, so this is going to be all the components in W will be independent Gaussian, zero mean unit variance. And then we're gonna take that W0 and we're gonna add a small number, 1e minus 6, times another random vector. So W1 is gonna be a very small perturbation of W0. And then what we're gonna do is evaluate both sides of this and print them out and make sure that they're close. So here, first evaluate J0, J gradient 0 by calling log fung with W0 as the input. Then J1 gradient 1 using the same function with W1. And then we can compute this thing in this line. That's the right side. And we're going to print out the left side and the right side. And you can see they agree to at least 4 decimal places. So since we're doing this with random W's, it's probably not luck that they're agreeing, right? It's probably because they are consistent. So this is highly recommended, especially in some of the labs, like the lab for Unit 6 is actually the most challenging lab of the whole semester. And it's really important to do this, to check to make sure that your implementation is working. Because if it's not, you're just going to get weird results, and you'll be asking, why isn't this working? Well, did you check your gradient? Are you sure your gradient is correctly coded? So this is how you do it. Okay. Any questions on this idea? Okay. All right. Okay, so we're finally ready to program gradient descent. So here's a function, gradient optimized simple. So this is what we give it. We give it the jeval function. That's the function that computes cost and gradient. We give it an initialization, vector W init. Typically, we just choose that randomly. We're going to give it the learning rate, which is what we've been calling alpha. We're going to use a fixed learning rate. So you can say alpha k equals alpha for all k, just a fixed number. And then we have to tell it how many iterations to run. We're going to run it for 1,000, and then we'll take a look at the curves that come out of that and see whether we need to run it for longer or not. And then this code is going to return the final parameter vector that it found after 1,000 iterations. It's going to return the cost of that final parameter vector, and it's also going to return this history structure. The history structure is going to contain a history of the W vectors as well as a history of the costs. And that will, if we want to do some debugging and figure out what happened while we were optimizing, we can take a look at those history elements. So the code is really not too complicated. So the very first thing is we take the initialization in W init, and we set that, we assign our W vector to that. So the W vector is now just going to be the vector that we keep updating as we go through the algorithm. It's going to track where we are on the cost surface. Here's a for loop. This is a for loop over, so we're using the iteration variable it, and this is range init. So it's going to start at 0, go all the way up to init minus 1, so a total of init iterations. At each iteration, at the current parameter vector, we're going to evaluate the cost and the gradient. And then here's our gradient descent step. The new W vector equals the old one minus the learning rate times the gradient. Simple as that. And then we store J0. We basically, there's different ways to do this. Here we're using the append function, so it basically takes the J part of the history and then just appends one more entry onto the end. And we're also storing the W vector here. And we run this loop over and over for n iterations. And by the way, these are just defaults. So if you don't tell it the learning rate, it will automatically assign it 1e minus 3. But you can, of course, assign it different numbers if you like. Okay, so when we're all done with this, it turns out that these are not NumPy vectors. And so we're going to convert them to NumPy arrays. We just go through the two things inside this history, and each one of them, we're going to turn it into a NumPy array. And that's going to make our life easier if we want to plot it and so on. So finally, we're going to return the parameter vector it found, the cost, the final cost, as well as our history. So again, the main step is really this one. Okay. All right, any questions? Is this making sense? Question?
This J eval is the first function we create, right? Not the class.
Yeah, so what we're gonna, this is gonna be the function, we would pass in, for example, this. Okay, all right, any other questions? Okay. All right, so let's take a look at what happens when we run this. So we're working on our logistic regression. That's what we coded. We're going to initialize. There's different ways to deal with random numbers in Python. I think this is the recommended way now. You make this RNG, this is random number generator object. Once that's instantiated, you can create a new random number from it. This is using the standard normal distribution. This is going to be a vector with d+1 entries. By default, unit mean, 0 variance. So this is going to be our winit vector. And so here's the function we just talked about. We're just going to rename this jeval, and then that's what we're going to give to our gradient descent code. We're going to use 2,000 iterations, a learning rate of 1e minus 4. You can see those are what we're passing in here. And we run our code. So it's going to iterate for 2,000 times, and finally when it's done, it's going to return those. And then we can plot everything here. Let's first make a vector of t's. These are the iterations starting at 1 and going up to 2,000. So that's just going to be a vector that we can use to plot on the horizontal axis. And it often helps to plot these things on a log scale. So notice that we're plotting iteration logarithmically. If you don't do that, essentially what happens is all the interesting stuff happens at the beginning, and then it looks like the thing is very constant for a long time. If you plot this horizontally in the log scale, it's often easier to look at. The loss, actually we're plotting the loss also in the log scale, because loss is something that can span orders of magnitude. So if you don't plot it in a log scale, again, you could get a very boring kind of plot that looks like this, which is hard to figure out what's really happening. So we're using a log scale here, log. And we're plotting a grid and labeling the axes, that's always a good thing. So what we find is that the loss is decreasing, which is good, right? That's a good sign. If we would see the loss increasing, what would that mean? Was that?
Wrong code.
Wrong, it could be wrong code, but it could be something else. What else could cause that? Large alpha. The step size was too large, right? We're overshooting. That's another possibility. If that's the case, we would return and choose a smaller learning rate. We'll actually look at what happens with larger learning rates in just a moment. But everything looks pretty good, except what would you say is kind of the main issue here? What's unsatisfying about this that might say we need to try again? What do you think? So I would say
Maybe we want more horizontal at the end.
more what at the end?
Horizontal.
Yeah, we want to see that the loss has sort of stopped decreasing if possible. And so it looks like things are still increasing, which suggests maybe 2,000 iterations isn't enough. Maybe if I'd run it more iterations, I can get a much smaller loss. So, But on the other hand, I'm not sure how long this took, but maybe we're kind of impatient. Maybe we're working on a slow computer. Maybe this took us like 5 minutes to run this, and we're like, no, I don't want to use more than 2,000. So, that's another thing. Maybe we need to try to improve the algorithm. So we're going to try to do that as well in the future. But at least we can see things seem to be working, although it doesn't seem to be finished optimizing, and the convergence maybe is kind of slow. Maybe we can use a slightly more advanced variation of gradient descent. The other thing we can do as a sort of qualitative way, I guess there's one qualitative thing here is what is the value of the loss? We've decreased it to, this is 100 here, so decrease the loss to, I don't know if that's 50 or 40. Another qualitative way we can measure the performance is to take our W vector and actually use it for prediction. Use it to see what is the test error. So that's what we're going to do over here. So this code, what it does is it takes any X matrix, this could be our test samples, for example, or training. It takes some W vector. The very first thing it does is it computes a vector of scores, and then it thresholds the score. It says if the score is greater than 0, these parentheses make that a logical variable. And now y hat is basically going to be either logical variable, or you can think about it as like ones and zeros. So if the score is positive, that's good, right? We want the score to be positive in classification on the test samples. Sorry, if the true samples have a positive score, we want our predictions to have a positive score. So here's our predictions. And here's where we evaluate the accuracy. We take the vector of predictions, we compare it to the vector of true test labels, we see if they're equal, and this is going to give us a vector of, again, ones and zeros. And if you want to compute the accuracy, that's just the mean of that vector of ones and zeros, right? Like if we were if we were correct, in all cases, that would be a vector of ones. We would take the average of this vector of ones, and it would give us a 1, which means our accuracy is, the percent accuracy is 100 if it's a 1. On the other hand, if they're all wrong, we would get 0. And maybe if they're half right, half wrong, you'd have equal number of ones and zeros. You take the mean, you get 0.5, 50% accuracy. Okay, so this is a quick way to tell the accuracy. And we can see that at least for the parameter vector that we've achieved here, the accuracy is 96.8%, which we don't really know yet if that's good or bad, but it turns out we can improve it. So that will be what we want to do. The first thing we'll try as a way of improving it is let's see what happens if we choose other learning rates. Maybe we should revisit that choice. Okay, so the version on the previous page was the orange curve, this one. If we would have chosen a learning rate that's 10 times smaller, 1e minus 5, you can see we would have gotten the blue curve. So there you can see it's nice and smooth, but it's going even slower. Right? After 2,000 iterations, it's only at 100, whereas with 1e minus 4, it got down much lower. So you might say, well, what about if we use a larger learning rate, 1e minus 3? So I guess overall, it is working better, but notice what's happening here. What's happening in the first iterations, right? This is iteration 1, 2, 3. So what's happening in these first iterations? Overshooting, right? Cost is actually going up. So somehow, even though cost went up, it recovers and the cost goes down, but then the cost kind of goes up and down. It sort of alternates. For whatever reason, it does eventually sort of get better, and actually even does better than our 1e minus 4 eventually. Now you might say, okay, it was a good thing to increase the learning rate. Maybe I should increase it even more. So let's just increase it by a factor of 2. And now you can see things are really going crazy. And it's overshooting quite a bit, and then somehow it's stabilizing and then overshooting and so on. But there's so much overshooting going on that it's not doing as well as this learning rate 1e minus 3. So you can see here sort of the trade-offs between learning rates that are too small, learning rates that are too large. Clearly the learning rate is super important to getting it to converge quickly, but it's not necessarily an easy thing to pick the learning rate. Here we're doing it with trial and error. That is one way to do it, but we might wonder, is there a more automated way of choosing the learning rate on the fly so that we don't have to play around as much? By the way, if we look at the test accuracy, we can see the effects of these different learning rates. So we can see that we are doing the best here for 1e minus 3. It's not that much better. It's, it's in the third decimal place better than the learning rate 1e minus 4 or 2e minus 3. Okay, so basically, learning rate is important. Let's try to figure out if we can improve, have a more automated way of choosing it. Okay, any questions on anything here? Yeah.
So usually in practice, which one is better, like to have like some overshoot in the beginning, but to have like less loss at the end, or the smooth loss from the beginning and you have an overshoot?
In this case, if I had to choose among these, I would choose the green option because it really is giving the best loss at the end. But what this means is that if you run it from different random initializations, that sometimes the initialization could be bad, or you might get a lot of crazy stuff going on, and maybe the next time you run it, maybe it doesn't work so well. So it could be a little fragile. So that's another reason you might be kind of suspicious whether at that learning rate you're guaranteed to get a good result, or maybe we just got lucky this time. Okay. All right, so let's try to do this a little bit more carefully. We're going to use something called the Armijo Rule, and we're going to adapt the step size. We're going to change it on the fly in a way that guarantees that the cost will decrease every time. So to explain this, we have to come back to this equation that we've seen a few times now, which is what we got from our gradient descent analysis. So here on the left side, we have the cost after the update equals the cost before the update minus this term that's linear in alpha, which is a good term. It's decreasing our cost. And then we have this quadratic term, quadratic in alpha, which is bad because it's increasing our costs. And we know, roughly speaking, that if alpha k is small enough, then this term will overwhelm this term, and we will see a decrease in our cost at that kth iteration. So this is the Armijo Rule. It's sort of a clever way to ensure that this happens at every iteration. So let me just sort of say what to do, and then I'll explain it later. So at every iteration k, what you do is you choose a step size. It could be the same one you chose previously or a different one. And you check if this criteria is satisfied. Notice that we have an inequality here. So this is like a binary thing. Either it was satisfied or not. And this is chosen in a careful way so that if it's satisfied, you know that your cost has decreased. You should accept that step. You should say, that's a good step size, I'm going to use it, and move on to the next iteration. You do the update and everything. However, if you find that this criteria did not pass, then you say, okay, this step size is too large. I'm going to throw it out, and I'm going to decrease my step size and try again. So I'm not going to do the update. I'm not going to compute the new W using that old too large step size. I'm going to pretend that I never, tried that. I'm going to try a smaller step size. So that's basically what we're saying here. So if this Armijo Rule passes, you accept WK plus 1. And in fact, you might say, well, you know what? Maybe the step size I've been using is too small. Maybe I could go faster. Let's try. So what you do is the next time you increase the old step size alpha k by multiplying it by some number, usually just a little bit larger than 1, maybe like 1.1 or something. So that way, if you somehow start out with a step size that's too small, you'll gradually increase it and increase it and increase it and increase it until you find it's too large. And when it's too large, this is what you do. You decrease it by multiplying it with some number that's less than 1, maybe 0.5. So at every iteration, you evaluate this. If it passes, you accept the step, and you increase the step size for the next time. Otherwise, you reject the step, And you retry that step with a smaller step size to see if it will pass under a smaller step size. If not, you decrease it even further, and so on, until it finally passes. Okay. So that's the idea. The main thing is to understand what's going on here. So first of all, there's this number c, which is some number between 0 and 1, and it's a design parameter. It's going to affect how well this works. Typically, we can just set it at 1/2, and that works fine. Okay, so what else is going on here? So this, if it wasn't for the c, this is exactly equal to the first two terms. Okay. So there's a picture that I think helps to explain what's happening. So here's the picture. So what we're showing here is, like, this is showing the cost after you take a step as a function of the step size. So as you hear, as it makes sense, if the step size is really big, oh, and by the way, the 0 line here, this is like the cost, the old cost, JW. Okay. So if the new cost is above this line, that means you overshoot it, right? It's the new is greater than the old. That's a bad situation. And you can see that's happening for large enough alpha. Right? And the reason why I drew this kind of shape like this is to emphasize the fact that this is sort of the quadratic term. What's happening here is eventually, there's this quadratic dependence on alpha k, and that's what's making this shoot up. Now, if you focus on what's happening with small alpha k's, then as we know, this term is really small. And so in this region, you can just explain what's happening with this term. So that's this dashed line. Right, so the dashed line is an approximation to this red curve that holds for small alpha. So this thing here is exactly this dashed line. It's like the linear approximation to the new cost where we're talking linear and alpha. Okay, so the way the Armijo rule works is it constructs this new, its criteria is actually this blue line. So the difference is in the criterion, there is this C, and what C does is it takes, so if C was 1, then you can see that the Armijo criterion is nothing more than this linear approximation. But what happens is as C decreases, this line starts to tilt upward. And so when C is 0.5, that's what this thing is. This is just a fancy name for this whole thing. We'll call it y sub c alpha k. When C is 0.5, this has moved up to here. And maybe that explains why, if your update, so the value that you get after your update is going to be somewhere on this red line. So you can see if that is less than or equal to this blue line, you're good. You've definitely decreased your cost. But if it's greater than the blue line, so that would happen anywhere over here, there is some danger that you have increased your cost. So by choosing this C, you're choosing the angle of that line. So for example, if you chose C equals 0, the blue line would move up to here. And then the Armijo rule would simply ask, did you decrease the cost or not? By moving the blue line down here, you're being a little bit more stringent than just saying, we've decreased the cost. You're saying, I've taken, okay, so the optimal would be right here, right? This would be the optimal alpha. This would be like the alpha that minimizes the cost after we take a step. So we're saying we don't even really want to overshoot that optimal alpha too much. Like all the stuff over here, we don't want to do that. We just want to stay in this region between, this kind of linear type behavior here up to near where that optimal alpha is. Okay, so this C is a design parameter. We can change it, but 0.5 is the typical number that people use. Okay, so is this making sense, what we're doing now? At every iteration, we have some guess of what alpha k should be. Based on that alpha k, we actually do the update. We measure the cost after the update, which is going to place us somewhere on this red line, a red curve. We also evaluate this, which is easy to do because if we've taken that update, we know our gradient, we know our cost. So we get those two values. And if the red curve, if the point on the red curve is below the point on the blue curve, Armijo Rule says good, accept that. On the other hand, if the point on the red curve is above the point on the blue curve, Armijo Rule says nope, step size is too large, decrease it and try again. So in that case, you would decrease it, maybe cut it in half. You try again and say, oh yeah, this time it worked. So that's how this Armijo Rule is working. Does that make sense? I know it's a little bit convoluted. Questions? Yeah.
C still seems kind of, it's very arbitrary, right?
It has to be between 0 and 1.
Right, because if we're comparing against our blue line slope, but if C doesn't really, if there's no logic to really set C, are we really doing anything effective at the end of the day, I guess?
Well, at the end of the day, for any C between 0 and 1, you're guaranteed that your cost will decrease every time. So C is more like a tuning parameter. Like if you set C well, it'll go really fast. And if C is, so think about what happens if C is very close to 1. Then your blue line is like this, and there's a very small range of alphas that are going to work for you. So you're going to be constantly adjusting alphas in that range, and you won't even be decreasing your cost very much, right? Because it's just this really small alphas. So that's probably not going to work. And if C is close to 0, then you could be overshooting the optimal quite a bit, and you could be going getting small decrease that way. So that might not be the best. 0.5 is sort of this nice happy medium. It just tends to work pretty well. So you don't have to stress out about choosing it. Just set it at 0.5 and be happy with it. Yeah. Okay. But is the idea kind of making sense? What's happening, or any questions on? You need me to try to explain it again? It's good? Okay. So there's two other numbers, as we said, to choose. You have to choose the beta increase, beta decrease. I find that number like a little smaller than 1, like 1.1 works well here. And then a number, significantly smaller than 1, like 0.5. Because the problem is if this fails, there's wasted effort in the sense that you have computed a gradient and a new cost, and you have to throw out that computation because it was useless. So you don't want this to fail too much. Like if it fails half the time, 50% of the time, that means 50% of your computations are wasted, right? And given the same number of total compute time, you could have taken twice as many steps if your steps all passed. So there's a cost to this failing in terms of wasting computations that you don't want to do. So that's why when it fails, you want to make a big decrease and say, okay, let's be conservative, let's make it a lot smaller, and we'll gradually make it bigger. Because if it's too small, maybe you haven't gotten a very powerful step, but at least you could take a step, and the computations you use were successful. So that's why I think this one should be closer to 1, and this one should be farther than 1. Okay, another thing sometimes students ask is, well, why don't you just try a whole bunch of different alpha k's. Just make a grid of alpha k's and try them all. And then find the one which worked the best. So maybe if we tried those alpha k's, we would find that this one gave the biggest decrease. And yeah, so that would give you like the most powerful step, right? But what have we lost in doing this? Why is this not ideal?
Steps.
Because we had to try all these, in this case, like 8 options, right? We could have taken 8 steps. We're only taking 1 step in the end. We could have taken 8 steps. That could have made a lot of progress, but instead we were like trying to so carefully make this step perfect that sometimes it doesn't help to be a perfectionist. Okay, so the point with Armijo, it's very efficient. If you don't fail your step, you will make some progress every time. And if you're failing a small proportion of your steps, it's still very efficient. So even though it's a simple idea, it's an old idea that's been around for, I think, 50 years or so, it's still used quite a bit because it's simple and it works. Okay, so yeah, so this is the idea. You could imagine trying a bunch of different alpha k's and choosing the best, but it's just a lot more expensive. And at the end of the day, if what you really want to do is speed things up, you have to be really careful and not waste computations. Okay, any questions? Yes.
This is just one curve, like for one omega, right?
You mean one W?
One W, yeah.
Yeah, this is, so we have a vector of W's. We're always updating our entire vector at the same time, like all the coefficients simultaneously. And this is for one iteration K. So we do this at every iteration.
I mean, that's why you said you don't, like a simple idea, don't search for the optimal alpha, because you have to search for every W, right?
Yeah, let's think about what you have to do. For every new alpha, you will get a new WK plus 1, and then you will have to compute the cost there. And that computing the cost means running through, all these steps of our code here, which involve taking matrix multiplies and stuff, which can be expensive when you have a lot of data. So it's like every time we do this, we want that to really count, be able to use it, not just a wasted computation. Okay. All right. People pretty good at this? Okay, let's see what happens when we run this. So the code is not very difficult. Here's the Armijo condition. Just check if this passes. We update our W's. So we can think of this W1 as like a temporary W, and this J1 and J grad 1. These are temporary quantities. We're not sure if we're going to accept them. If this passes, we do accept them. So we set W0 at W1, J0 at J1, gradient at gradient 1, and so on. And we also increase our learning rate a little bit, just so that we can increase it if it's too small. However, if it fails, we basically throw out the W1 and the J1 and the J grad 1, but we do decrease the learning rate. And then we try again. With that learning rate, we try to take another step, which means we have to call J eval again, and so on. So this is what happens if we plot the loss as a function of iterations. We see that after 2,000 iterations, this has gotten pretty horizontal, right? Which suggests that yes, probably done converging, or very close to it. And it's also interesting to look at the learning rate as a function of iteration. You can see we started here at 1 e minus 3. That was actually too actually it was too large. And we cut it in half. And notice that our cost didn't increase at all, because basically from here to here, we didn't update our cost or our loss. We just kept it the same. So we tried decreasing it, and even that was too big. So we decreased it down here to 0.25. And that was small enough so we could take a whole bunch of iterations, progress. But all of a sudden, that was too large. So we decreased it. That was good. Increased it, decreased it, and so on. And as you can see, it ends up, oscillating. But what's interesting is that eventually it sort of increases. Originally this was 1e minus 3 was too small, but eventually it looks like we want learning rates in that neighborhood. So this, by increasing things a little bit, we can sort of figure out as we go what is the right learning rate. That's changing as we go through our loss function. Okay, so our loss is smaller than before, test accuracy is larger than before, and and the way this is coded, this is gonna in 2,000 of these steps, because these 2,000 are counting all the bad steps. This is a fair comparison against the other method. Okay. All right, any questions on Armijo? Okay, so we just have convexity to talk about, and we'll save this for next time. We'll go through it pretty quickly, but we're out of time for today. So, and then next time we'll get into the next unit, which is a support vector machine, which is another look at classification that's more sophisticated than logistic regression. So see you guys on Wednesday.